And here we go. This is a table of it again. So mass of sample and test tube, mass of the evaporating basin, mass of the filter paper, mass of filter paper and sand, and mass of evaporating basin and salt, and then the original mass of the sample tube, so the tube that all the contents came in. Here are some sample measurements. So if we were to do this, this could be one of many sets of data that you could get out. How do we calculate how much sand and salt we have? We take the mass of the mixture. So how much mixture do we have? Well, that's easy. It's the total mass of the tube minus the mass of the test tube. Okay, so the tube plus all of the mixture minus the weight of the tube gives you the weight of the mixture. And that's M1 minus M6. If you go back and look at the table again, that will tell you what each part is. And we'll call that M7, or we could just call it mass of mixture. M7 is just easier to write, that's all. So the mass of the sand, remember what we measured. This is key. We have to think back to what we measured and what we want out. What we measured was the mass of the filter paper plus the mass of the sand. That was M4. We have weighed the mass of the filter paper previously. That's M3. So the mass of the sand is simple. It's just the mass of the filter paper plus the sand minus the mass of the filter paper. And so M4 minus M3 gives you a particular number based on the numbers that we got before. The mass of the salt, again, we've got the mass of the evaporating basin. We measured that. We've got the mass of the evaporating basin and the salt together. So you just take the mass of the evaporating basin away from that mass of the salt and basin, and you've got the mass of the salt. It's M5 minus M2. And finally, the mass of the water is fairly easy if you think about it. Well, if we have the mass of the mixture that has water, salt, and sand, we've got the mass of the salt here and the mass of the sand here. So if you just take them away from the total mixture mass, that will give you the mass of the water. And that's just a simple way, if you just think carefully through each measurement and each calculation, it's just simple additions and subtractions, mostly subtractions in this case. The key part in this experiment is remembering why it seems convoluted. Why did we weigh the filter paper and then measured the filter paper and then weighed the evaporating basin, then weighed the evaporating basin and salt? The reason why we do all this, and the reason why scientists seem like they're doing really convoluted experiments, is because we want to reduce the error. Error is important. If we've got bad error, if we've got lots of error, then our results are essentially meaningless. If I tried to scrape all the sand out of the filter paper and then tried to scrape all the salt out of the evaporating basin and I tried to do all this fiddly stuff, one, that seems like a lot of work, but two, it's very hard to get all of it. It's almost impossible. How could we ensure that we cleaned out the bowl very, very well or cleaned out the filter paper perfectly? We can't. So we have to kind of compensate for that by weighing a few more things and then just using our knowledge of mathematics to take them back and then get to the original result that we want. So that's why it seems like it's lots of extra steps, but those steps are important to reduce the error. Okay, so the percentage by weight is just a fraction times 100%. If you went to the data, it would just be 1.467 grams over the total mixture mass times 100, and that's a percentage, and it's 20.7%. Same, you can do the exact same calculation for salt, just put the number for salt here, the mixture mass stays the same, and you get 45%. So it's more salt than sand in this case, so there was probably more water than sand in our particular experiment. It may not be the same for you, but that's for this one. And for water, again, you can do exactly the same calculation. So just the mass of the water over the mass of the mixture times 100, and that's the percentage by weight of water in the mixture. There's lots of different percentage measures you could use. You could use percentage measure by mole, percentage measure by atom or something. You can use any measure that you want, but the reason why we say percentage by weight, even though it seems obvious, is we want to ensure that everyone's on the same page. We want, say, a scientist in Germany or a scientist in Denmark to be able to replicate this experiment and get exactly the same number. So we have to tell them, what are we actually measuring? Are we measuring the weight, or are we measuring, say, the number of moles? Okay, so that's why it's percentage by weight. It seems obvious, but just remember that there are lots of other ways to measure things in science. So that's why we tell you this. And it's 3.8%.